Hi, welcome to my channel. Today, let us understand an important issue in deep learning called vanishing gradient problem. Here, we are looking at two activation functions, sigmoid and tanh, along with their derivatives. For sigmoid function, sigma x equals to 1 over 1 plus e to the power minus x, and the derivative of it, sigma x times 1 minus sigma x. For tanh function, tan h equal to e to the power minus e to the power x minus e to the power minus x over e to the power x plus e to the power minus x, and its derivative is 1 minus tan h square. These derivatives play a crucial role during backpropagation because gradients are multiplied by layer. Now let us focus on sigmoid saturation regions. When the input value x goes to positive infinity, sigma x tends to 1 and its derivative becomes 0. Similarly, when x goes to negative infinity, sigma x tends to 0 and its derivative becomes 0. This means that for every large or very small inputs, the gradient becomes almost 0. Now let us see the same issue with tanh activation function. When the input magnitude becomes very large, tanh tends to plus or minus 1. As a result, its derivatives also become 0. So even though tanh is zero-centered and greater than sigmoid, it still suffers from saturation for large input value. This again causes a gradient to vanish during backpropagation. Now summarize the saturation condition. Both sigmoid and tanh saturate when absolute value of the input is very large, that is, modulus of x is much greater than 0. In such cases, the gradient is nearly 0. During backpropagation, gradients are multiplied across layers. So if each layer produces a very small gradient, the final gradient reaching the early layers becomes almost 0. Mathematically, the absolute of del A del x is much less than 1, which implies backpropagated gradients vanish. This is the main reason why sigmoid and tanh are avoided deep hidden layers. Instead, the modern deep network prefer activation function like ReLU and its variants, which reduce the vanishing gradient